Welcome to this explainer. If you're a focused learner looking to figure out how massive, highly complex operations actually run flawlessly, well, you're in exactly the right place. Today, we are unpacking the sheer 24/7 chaos and complexity of running an Indian paper mill. We're going to trace the fascinating journey from a single customer order all the way down to the exact pulp recipe bubbling on the shop floor. Okay, let's dive right into our roadmap for today. We'll be looking at escaping the chaos, then master scheduling, capacity and materials, the art of scheduling, executing orders, and finally, the transformed mill.
Part 1. Escaping the plan and chaos and moving beyond spreadsheets. You know, in the high-stakes world of paper manufacturing, there is literally zero room for guesswork. I mean, we're talking about machines the size of city blocks running continuously. A single miscalculation, maybe relying on some tribal knowledge or a disconnected spreadsheet, it can disrupt the entire plant's output. The old way? Manual Excel planning. That meant a sluggish 7 to 10 day cycle, a frustrating 20% material shortage rate, and just massive amounts of time wasted switching between paper grades. Compare that to the automated Papyrus BPApp. It cuts that cycle time down to an incredibly fast 4 hours and boasts a 95% material availability. It's essentially replacing chaotic guessing with lightning-fast, system-enforced efficiency.
Section 2. Forecasting and master scheduling, the macro view. So, before a single sheet of paper is even made, the new system has to aggregate a massive amount of raw data to build a proactive bird's-eye master plan. And it does this in 4 systematic steps. First, we consolidate the demand, pulling in open sales orders and regional forecasts. Next is forecast consumption. This is where actual orders consume the forecast so, we don't accidentally double count. Then the system generates the actual master production schedule, which smooths out demand spikes, like the ones you get around Indian holidays or seasonal shifts. Finally, the whole plan goes to restrict approval workflow so it becomes an actual executable target.
Now, you might be wondering, what exactly is that output? An MPS, or Master Production Schedule, is basically your time-phased production plan, perfectly optimized for maximum machine utilization. And the logic here is absolutely crucial. The system strictly enforces a minimum 8-hour run length for any paper grade. Why? Well, because changing paper grades brings steep costs and just inevitable waste. You absolutely have to amortize that by running in long, uninterrupted blocks.
Which brings us to a really brilliant concept: the schedule freeze. To protect the crews and the raw materials that are already staged out on the floor, the timeline gets increasingly rigid. 2 to 4 weeks out, the schedule is firm. 2 weeks out, it gets what we call slushy, meaning changes need planner approval. But exactly 24 hours before execution, boom, the schedule completely freezes. No changes allowed. Period. Well, unless top-level management steps in to override it.
Moving on to Section 3, Capacity and Material Planning, the reality check.
Okay, let's see how this builds. We have our ambitious master plan, but now we have to validate it against actual physical constraints on the ground. Our target capacity utilization is that sweet spot right between 85 and 95%. But if machine speeds and scheduled hours push demand past that 100% threshold, we're in an overload scenario. The capacity requirements planning system proactively flags these bottlenecks before they ever happen, keeping the plant from overcommitting and ultimately ending that nasty cycle of late deliveries. But here's the catch. You also have to have the right materials actually on hand. Enter Material Requirements Planning, or MRP. This takes the MPS and explodes it through multi-level bills of materials, basically the master recipe lists, calculating the exact raw material needs based on strict lead times. It guarantees that you don't fire up the massive digester without having the exact right chemicals on site. It permanently eliminates those historical 15 to 20% material shortages. Just a total game changer.
Let's take a look at a typical pulp blend recipe for an 80 GSM, or grams per square meter, copier paper. You've got your hardwood, softwood, filler, and sizing. But the most fascinating part is actually that negative 10% broke recovery line. Broke is just the industry term for damaged or off-spec paper. The system proactively calculates that this waste paper will be recycled right back into the pulper, dynamically reducing the amount of virgin pulp you need to order in the very first place. It's incredibly efficient.
Section 4. The art of scheduling, the butterfly effect on the floor.
All right, let's zoom in a bit to the specific shift level. This is where all those macro decisions finally hit the complex, noisy reality of the shop floor. The system dictates some very strict sequencing rules. Production has to flow from light to dark colors. So white, then cream, yellow, pink, and finally your dark colors. Think about it. If a manual planner accidentally goes from a dark brown back to a crisp white paper, it forces 30 to 60 extra minutes of brutal machine wash time. By automating the sequencing, that wasted time is completely eliminated.
And that strict structure, it extends to the chemistry too. All that scattered tribal knowledge is replaced by hard system rules tied directly to biz quality standards. Dangerous combinations, like mixing alum and AKD sizing agents or OBA brighteners, are flagged with hard stops. The system literally prevents them from ever being dosed together at the wet end of the machine.
So, what happens during a mid-run shift handover when the machine literally never stops running? It's a great question. The answer is a mandatory dual sign-off checklist. Right at the 6, 14, or 2200 shift change point, both the outgoing and the incoming supervisors must digitally capture machine tension, speed, and paper moisture. It ensures nothing falls through the cracks, even at incredibly high speeds. Section 5. Executing work orders, from plan to paper. Now that we have our sequence totally locked in, let's explore how the system translates that schedule into step-by-step instructions for the machine operator. Every single work order follows a strict flow: created, released, materials issued, executed, and closed. What's really clever here is that during the materials issued phase, the system allows for a plus or minus 5% tolerance. This perfectly accommodates the sort of organic variations you see in real-world papermaking, like needing slightly more pulp because of moisture differences, without breaking the system's financial tracking.
Less than or equal to 2%. That number represents the strict maximum scrap limit for paper reels. So, instead of abstract management goals about quality, the system turns that into a hard, trackable, and enforceable metric on every single work order.
On the flip side, what if a cost variance exceeds 10% between the planned costs and the actual executed costs? Well, that's a major problem. That triggers a critical red alert in the system that actually halts the closure of the work order entirely. It just freezes it, right then and there, until senior management steps in to investigate the financial leak.
But let's be real. What happens when a machine suddenly breaks down mid-run, or you just unexpectedly run out of pulp? The system has this really clever exception rule called work order splitting. Basically, a massive 5,000-unit run can be paused, split into 2 completely separate orders, and then the rest can just be resumed days later. It's a brilliant bit of flexibility that prevents total plant gridlock when the unpredictable inevitably happens.
And finally, Section 6, the transformed paper mill, the power of structure. Let's bring this all together and look at the monumental business outcomes of adopting this end-to-end framework. If you ever needed proof as to why this highly structured digital leap is absolutely essential for taming a massive manufacturing operation, well, here it is. We are looking at 70% faster planning, 95% material availability, a massive 98% on-time delivery rate, and over 20% less waste during grade changes. And to put that into perspective, that operational efficiency connects directly to the financial stakes. Schedule-related waste costs, literally the money thrown away due to bad planning and unnecessary grade changes, are now strictly capped at under 2 lakh rupees, or about 200,000 rupees a month. That is real, tangible money saved simply through better structure. I want to leave you with a quote. If a 15-minute mid-shift handover can ruin a batch, how much invisible waste is hiding in your own disorganized daily processes? It's a provocative thought, isn't it? Take a moment to reflect on how this level of structural rigor could transform your own chaotic workflows. Thank you so much for joining me on this explainer. Keep learning, keep optimizing, and I'll catch you next time.